substituting k equal plus or minus square root of g over li. And before we substitute, let's simplify our notation a little bit. We got k equals plus or minus the square root of g over li. And I'm going to say that's equal to plus or minus omega I, where omega is just a simpler expression for the square root of g over L. Now, omega is going to have an interpretation, which you might already be familiar with. Interpretation is angular frequency or angular velocity on a reference circle, but we'll see what that means in a minute. So substituting plus or minus omega I for k, well, substituting each separately, we get two solutions. We get x1 of t equals a e to the omega t, let's make that I omega t, and x2 of t equals, now our substitution or our trial function was a e to the kt. A is an arbitrary constant, so I'm going to use b instead of a. Since the constant is arbitrary and I don't want to have the same constant for both of these solutions, I don't need to have the same constant for both solutions. So to keep things general, I'm going to denote this constant a little differently than this one. So anyhow, we have x2 equal b e to the negative I omega t. And our general solution then is x of t equals a e to the I omega t plus b e to the negative I omega t. Now, if we apply the Euler identity, we're going to get something that should be fairly familiar, should feel kind of familiar by now. We get a multiplied by the cosine of omega t plus I sine of omega t plus b times the cosine of omega t of, well, negative omega t plus I times the sine of negative omega t. And that's going to be a cosine omega t plus I sine omega t plus b times the cosine of omega t minus I sine of omega t, applying the fact that the cosine is an even function, so the cosine of negative omega t is the same as the cosine of omega t. The sine is an odd function, so that the sine of negative omega t is the negative of the sine of omega t. And then collecting terms, we have a plus b cosine of omega t plus I times a minus b sine of omega t, which then could be written as c, where c can be a complex number, times cosine of omega t plus d times I times the sine of omega t, where now c and d again are complex, and that can be written then as alpha 1 cosine of omega t plus phi 1 plus I alpha 2 cosine of omega t plus phi 2. And I've skipped the intermediate steps, which are identical to those we've previously seen. And once more, this is a solution to the equation. This is a solution to the equation. The entire expression is a solution to the equation. This solution is sufficient to specify the behavior of the pendulum if we know enough about the initial conditions. We can fit A1 and phi 1 to match whatever might be the initial conditions on this pendulum.